Well, I think most of you know Nicolas already, but I'll just do a brief introduction. He's a professor of statistics and data science at NSA. He's editor of Annals of Statistics, Biometrica, and JRSS. Actually, this is either past or present.
Past for this, yeah.
He's spent most of his career doing computational statistics, Bayesian statistics, including things like INLA, which has got an amazing amount of citations, but I'm told is way in the past. Now, a lot in sequential Monte Carlo. He also, of course, there's the Savage Award and the Degree Award for your book just a few years ago. And well, thanks to you, we also, I think, you were the real driving force behind the Pluses Demon seminar series. And I think that the fact that your connections and the fact there was a real warmth with you, I think, in a lot of the guests. And something I particularly liked was how earnest you were always in repeating the questions that people asked. You always made sure they were precisely asked. And so I'm going to continue that tradition. If anyone has a question for Nicolas, I'll very earnestly ask it here. So welcome and thanks for doing this.
Thanks for having me, and hi to everyone. I can see a few friends in the list of attendants. So hi guys, it's great to discuss with everyone. I have a cold, so sorry for I'm sorry for the voice, and I might cough a little. Sorry for that. I might say dumb things because of the cold. But anyway,
I think you're going to say some exciting, controversial things. Okay, but
I'll try.
We can start just with something very gentle. It's like,
let's go
what
gentle.
took you on your career as you did? Like, why did you choose to go into the direction of in academic and statistics? And
it's I hesitated a lot to do a PhD and to go to academia for different reasons, but I was a bit worried I was not cut for it. And I didn't do the direct straight road to a PhD. I started as a civil servant, actually. But I managed to find a first position where I could do a PhD, and I met Christian Robert, and that the rest is history. I mean, I think I found what Christian was doing super interesting, super exciting. It was just the right thing for me, and I managed to leave this position to a position as a lecturer at Bristol University in the UK, and came back to France as a professor position.
And what was so great about Christian and that was so interesting that made you give up your career as a civil servant? And
I mean, I was always a bit between. I mean, I always loved both mathematics and computer science, and in that what Christian was doing, you could see I could do a little bit of both, and I liked this. I think it was really for me this jack of all trades kind of thing, where you do a bit of math, a bit of computer science, statistics, also applied statistics. I really enjoy that in my job, doing a little bit of everything.
okay.
And I already told PhD students who wanted to work with me, is it the kind of thing you want to do, a little bit of everything? And some of them, like my previous PhD student, Dong, was really excited by that too. And he was right, because it was the right thing for him too. Mm.
Okay.
Mm.
And was Christian already a star at that point, or was it a bit early?
For me, it was. It's difficult when you're a student. You really know nothing about these things. I mean, the professor you meet is a star, and yeah,
I
I
think some
guess, yeah.
students know and some don't, actually. Like some have that sense. I didn't. Like I wasn't, I think, very
For me, it was
calibrated
someone who has
to.
already written books, so I have a lot
Okay.
of
Yeah, I
respect
think
for
I guess
people who
that's
write books.
that's
And,
a
yeah, yeah.
yeah.
And it was the end of the 90s, so I mean, it was not as I mean, the academia was not as international as it is now, and so he was pretty well known in France already, and yeah. Mm.
Yeah, I mean, I'm maybe it's not fair, but I feel France is not as Bayesian as it could be with
Actually, it's not so bad, and many thanks to Christian, I think. Yeah, these days it's quite. the community is reasonably big, I think.
Yeah,
There are a
okay.
lot of, maybe there are some people you might not know because they are more applied, but there are quite a few of these people actually.
Yeah,
And
okay.
yeah, no, it's not the UK, of course, but I think it's more than in Germany, for instance.
Yeah, that's true. The UK is unique.
Mm. Yeah. So
Um,
between, yeah, it's not so bad, but maybe in France it's mostly the computation. It's a lot of
but okay.
computation.
I mean, it's oh wait up. Have I not hit record? No, it is recording. Yeah, it's we're
It
good.
is. It is.
Um, so well, I mean, I partially was thinking with it that Laplace should be, I think, more celebrated than he is, but
Mhm.
um,
It is for other reasons.
in
Laplace.
France, people have dinner parties and they talk about, I don't know, Descartes and Proust or whatever, but that no one, as far as I know, people don't talk about Laplace in the same way. But I think
Uh,
he's there.
we have
Um,
Laplace streets and
um, uh, there's no slides today. Yes. Um, so, well, okay. Now you've spent quite a lot of your career on how to efficiently compute expectations under a posterior. So are you a subjective, objective Bayesian? What motivates that effort? Is it
if I want to be completely honest, I tend to treat this as someone else wants to compute this posterior, so let me help him or her to compute this posterior. But I'm not someone who think very carefully about the philosophy behind Bayesianism. Um, I like to work a lot with scientists, like in biology and fields like that, where they develop scientific models. And when you have a scientific model, the parameters have some strong meaning. They might have some scale. Then you might measure them in terms of seconds or meters. And then having a prior is pretty natural for these people. So then it's completely fine. So I like to work on this kind of application. And I think Bayesian statistics is particularly useful and exciting when you have a scientific model that makes sense for the scientist with perhaps too many parameters respective to the data. And then you have to be Bayesian. So I'm happy with that in the sense I'm happy that Bayesian ideas are really useful, at least in this scenario. For the rest, it's up to, I mean, I don't mind if people want to be Bayesian or frequencies in a given problem. If you have a very large data set and your parametric model is very simple, maybe the difference is not so big. And
okay?
I'm a practical
So
person.
it's a high dimensional. So you don't have like Definity Savage or Verse Jeffries or Fisher or Human
Yeah,
Case. Any of you're not going to say something controversial on you're a real believer in the conditionality principle or not.
I think that I mean, in the ideal world, we should be always Bayesians because, I mean, in a given situation, if you have a Bayesian answer and a MLE kind of answer, if they are different, which one are you going to choose? If they are the same, well, it doesn't matter. But if they are different, I think it's better
Okay,
to have a
but I mean,
it's better
even
to
the
have a
point.
post. Mm, mm,
I mean, you're so almost already talking about point estimation, which
mm.
maybe a Bayesian doesn't want to do.
No,
Also,
I mean, I
yeah.
really like the idea of having a posterior distribution of unknown quantities. That's really beautiful. That's very elegant intellectually. I like that, but I appreciate that it's sometimes too difficult to get that, and it's okay if you do logistic regression and using R, and just for certain problem, it's okay. I mean, I'm not.
Okay. And what do you have a steer of like when Bayes is worth the trouble or when it is not?
Um, I'm tend to be an optimistic person, so I guess it's getting still difficult to do Bayesian stuff for very, very large data sets. But then again, if you have a very, very large data set, maybe you have to end up doing something very basic anyway. So maybe you don't even have a model anymore.
Is
It's
it true to say Bayes is most useful when it's hardest to do?
mm,
Because
I would say so, actually. Yeah. If you could be Bayesian in this context, it would be great, I think.
yeah.
Yeah, because you need the regularity. The priors give you some regularity. All our colleagues who works on modern methods, they always add a penalty term, and our penalty is the prior. And in high-dimension problems, you need a prior or penalty in some way. So I prefer to think in terms of priors personally.
Okay.
Mm.
And when you're working on an application, when you sort of said, okay, you need it in high dimensions, but how do you choose the prior? Is it just Gaussian on everything, or or do you believe in elicitation and or something? You know, the
Right, as I
the
was
typical,
telling,
where does the
yeah,
prior come from?
yeah.
Which is, I think, where the philosophy is probably useful in trying to.
Mm, mm, mm. Well, as I was telling you, I enjoy working with more applied colleagues um, in environment science and stuff like that. And usually I rely on them on choosing the prior because again, in this context, it's quite natural to come up with reasonable priors. That's
I,
yeah.
if I'm going to add something, I mean, I think with setting priors, like people think it's like you're trying to set the range of the parameter, but often a more interesting and subtle thing is how parameters correlated with each other.
Ah,
Perhaps you
okay.
do it with hierarchies or something like this.
Yes, okay. Yes, sure.
Um,
Yeah.
but it's,
Yeah.
I mean, when people say where does the prior come from, it's clearly
Mm,
not
mm, mm.
nothing. Okay, so
Prior
nothing.
modeling is important, and I'm not the best person for that to discuss that. And I mean, there is Harvard Law has a more recent paper on setting priors around you have a certain parameter. When you set it at zero, it completely changes the nature of the model, and you want your prior to account for that. I forgot the name, but maybe someone in the audience should remember. But that's a beautiful paper on prior modeling. I don't work on that, but I can appreciate this kind of work, and this is the kind of thing we should do, I think. You
Right.
thinking about this term. So if you have nested models, you have to be careful that when you estimate the bigger model, it does not it does not pick the you always pick the bigger model just because of the prior. You see what I mean? So
Right.
yeah,
This maybe like it's similar to Occam's razor type
yeah. This
arguments,
kind of thing.
or
Yeah, yeah.
Bayesians do worry about things that I think are even hard to explain to non-Bayesian. Like also, there's also the if you're using a small model, is it a marginal of a larger model that you would use? That
Mm,
type of thing is, I think, hard to even explain to a non-Bayesian
mm,
why you're worrying about that type of thing.
mm,
Um, your approach, I think, I do think there's a certain school which I think of as Andrew Gellman as the icon of, is just as this is a best practice. Like too it's not too aligned to any philosophical school.
mm,
It's just this is best practice, and this
mm,
lets him do things like say, "Oh, randomization is just part of it."
mm,
Like,
mm,
are
mm.
you worried about randomization? Nothing.
No,
Okay.
in that respect, I think I'm quite close to Andrew's view. I'm happy with that.
I
But
think I remember there's an old paper of Monte Carlo is fundamentally unsound. Um,
because it's a frequentist algorithm.
yeah, but also
Mm.
why add randomness to something that does, what good does this do? And um,
Because Tony O'Hagan also made this point about Monte Carlo
it's his
being
paper, in fact.
yeah,
But there,
frequentist. Yeah.
and it was trying to come up with like more Bayesian ways of doing Monte Carlo and MCMC and things like this, which I think there's a lot of more modern work. It eventually took off, but
Mm, mm, mm.
um, um,
It's quite different, right? Because in statistics, the data is what it is. You cannot make it larger, but in Monte Carlo, you can make the sample size as large as you want.
yes,
That's a big difference. So,
to me that's a good way out. But even if like randomization and randomized controlled trials or A/B testing and things like
mm,
this, there is actually, I mean, it's true that strict Bayes is not consistent with lots of scientific norms, I think.
mm,
It's more radical. I,
Mm.
okay, in my view it is, but I think you just said you're more a shut up and calculate person who we can't
Yeah,
remember who said that
I'm a
it's,
bit like that. Yeah,
you know,
I don't
okay.
always shut up, but I shut up recently.
Okay, well then maybe we should jump to something that is more in your wheelhouse, which is Monte Carlo versus deterministic approximations.
Yeah.
Um, which is the way to go?
Okay, I'm very happy you asked this question because I try to work on both, and I'm very happy I did that. Again, I think I should thank Harvard Rue because working on with Inla really opened my eyes on many things. And on the one of these things is the appeal and interest of deterministic methods. But so I mean, I was I think it's a bit a shame that a lot of people working on MCMC never look at this approximation, which is a bit silly to me because you could at least use this approximation to get a first sense of the shape of your distribution, uh, even if you just use it to initialize your MCMC sampler, or maybe to have an idea or to set the covariance matrix of your random walk metropolis algorithm. At the same time, I'm a bit frustrated by all these papers on variational inference. They always repeat the same sentence. Oh, MCMC is slow, so let's do variational inference instead. It's a bit like a tired cliche. Omiros Papaspilios has great papers where they actually compare variational inference on Gibbs on certain hierarchical models. And it's not so clear cut. So I think it's really important to try to work, to be aware at least of what is going on both sides of this. And I do think that, yes, quite a few things are worth investigating a bit more between the connection between the two. But even if you work only on one side, you should be aware what's going on the other side. And especially in MCMC, people should a bit more should use more often these tools because sometimes when so sorry to cite my own papers, but in the Leaf Pima Indians alone paper, which at some point you're going to mention, I'm sure. One of the points we wanted to make is, guys, Metropolis is really bad. Random Metropolis is terrible unless you calibrate it properly, and then it's actually pretty good and difficult to beat. So of course, if you do this comparison that, oh, I want to do Gibbs sampling, or I want to do Hamiltonian Monte Carlo, but you compare to a poorly calibrated random walk, it's going to work terribly. But if you're in a simple model where getting a variation approximation is not so difficult, it's going to be super fast, or even maybe just Laplace. Laplace approximation, you get the answer is like 1/10 of a second, and then you know the shape of your, if your posterior looks like Gaussian, you can estimate the mean, the covariance matrix. You use it to calibrate random walk metropolis. It's a completely different story. To beat random walk metropolis, in my experience, you need dimension at least 100 or 200. So that's the kind of thing we were trying to
Okay.
say with Leave the Pima Indian uh,
That makes
paper a
you sound
lot.
like a statistician. Dimension 200 is high. We'll
So
get to difference in
that's the
machine learning.
yeah
Yeah.
that's the other issue we had when we wrote this paper is that we were a bit critical of these papers who were running example where like the Pima Indian dataset where the dimension is 9 and for these datasets the Gibbs sampling works okay. Gibbs sampling works okay, but random walk metropolis or even important sampling works well too. So why would you do a specialized algorithm because keep sampling is very specialized. You have to change it if you change the prior, for instance, if you can do important sampling.
Yeah.
Hmm. So yeah. No, so I like both, and I would like people to pay more attention to both sides between deterministic and Monte Carlo things.
I was never super into like the stats community, but back in Kerry Manguson's group in QUT, I remember it being like a real point of debate, and because I think it was, and in fact, reversible jump, which I've never heard anyone talk about for years, was
Mm,
the very fashionable topic at that point. And in that group, it was the deterministic people were always a bit embarrassed. They were like, "Oh, it's not exact," and maybe because they were the more dominant. And then when Bob Carpenter um, came and did. He kind of did the last Laplace's demon that we did fully. He said some real, to me, old school things that were back from that era of MCMC is really accurate. And I mean, of course, it's something the Monte Carlo people have is it converges to
mm,
uh, to a point, but it's a very niche in a little debate in the community, I think, with
mm, mm,
very
mm.
strong feelings. Uh,
It's really case dependent. I mean, the whole appeal or the whole motivation for INLA, for instance, is that yes, these methods they are biased, which is a maybe silly word to say they are approximate. But the time you need to determine the approximation error using MCMC is so large that it makes no practical sense. So yes, you have an exact method if you have an infinite amount of CPU time, but if you need days or weeks to actually determine the approximation error you make, where your approximation is takes a few seconds, a few minutes, it's so you can be an idealist and say, of, I still want to know the approximation error, but are you ready to run your MCMC amplifier for so long? If you do, that's great. But but again, what I've just said about TINLA is very true for some classes of model that have been explored extensively by the INLA team. And of course, you cannot say that in general. I mean, each class of models is a slightly different story with different properties for MCMC and data, different type of approximations. There's still work to do actually to better understand which one work better and why and what does it mean.
Do you have a feel of like if you're working on an applied problem, I'm going to use sequential Monte Carlo, or I'm going to use variational Bayes or Inler or Hamiltonian Monte Carlo? Like what's your do you have a guide, a rule of thumb of where to go and what to do?
I really enjoy people coming to me and say, "Oh, I have this problem. What will you do?" And I tried this, and I try to come up with. It's nice because in we have so many methods, and so it's like a big toolbox. But um, it will be. I guess there's an algorithm here to some kind of like tree structure. So if you have this, do that, etc. But it will be difficult for me to make it completely explicit. But um, yes, um, I need to think about it actually. But yes, I tend to recommend SMC tampering a bit by default for many problems where you have no idea where is the posterior. It might be multimodal, and you try to do some kind of Gibbs sampling, but it got stuck. So then I tend to recommend tampering SMC a little bit by default. Or if it's super slow, I might say, have you tried to look into variational inference, expectation propagation, etc.
Okay.
But but again, it might depend on the model. There are models where one method makes more sense than the others, and yeah,
I'm already thinking there's maybe a selection effect of what who comes to you and who you're talking to. Like
of course, yeah, yeah,
I mean, we joked just before that we started with like training an LLM or training a recommended system. You have a different scale of problem, much more data, and
yeah.
you need a kind of a SGD family of algorithms, really. Or
Mm, mm,
maybe there's,
mm,
uh,
mm, mm.
uh, but I mean, I guess you're getting a kind of modest but high dimensionality here, and maybe many modes, and you care about the modes. What do you care about? Is that what's implicit with SMC? Like why do we care about SMC? It seems you want to get all the modes or most of the modes, and you may or may not want the marginal likelihood.
It's a good question. It's I think multimodality is a fun is a weird problem actually because people come up with algorithms for multimodal posterior, but they test it on mixture distribution with different modes at the same height. I think in practice, we have posterior that are multimodal, but the modes will never be at the same height. And if you manage to reach the highest peak, that might be good enough in most cases because the other modes might be negligible anyway. So I always find it a bit strange, this obsession with multimodality, because
It,
we have we seen it in the wild. So,
but
so-
you're talking about the posterior of a mixture model, not the target
no,
being
no,
the
no,
mixture
no,
model.
no, no, no. I mean, there are many papers that illustrate their method on an actual mixture. Like
They
the,
just
the,
say the
the
posterior
target
is a
is a
mixture. Okay,
probability one half a Gaussian and one half another Gaussian, which is far away.
okay, okay.
And that's super tough because you have two modes that are very
Yeah, okay.
separated, but have the same
It's kind of a
height.
benchmark. This is a kind of toy problem, all the same, but
Yeah, it's a
um,
challenging one, but is it really something you might expect in true posteriors? I
well, I
wonder,
mean,
but
it's a bit less toy, but I think it's a bit standard. Of the posterior of a mixture model also is
mm,
highly multimodal. I assume that's another target that of this.
mm, 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 mm. But
Um,
yeah, I tend to like. Okay, let me rephrase my answer. I think I tend to recommend tempering SMC whenever you have reason to believe that you came up with a MCMC scheme that is slow mixing. And by introducing this tempering exponent, you can use more or less the same MCMC scheme, but it's going to mix much better at the beginning of the algorithm when the exponent is small. So maybe the temperature is high. That's the kind of recommendation I do. So
okay.
often
I've
people come up
yeah,
with problems like that. They can come up with a Gibbs sampler maybe, but the mixing is terribly slow. Mm. And
okay,
so
okay.
so yeah. And it's not, I'm not sure, we're not even sure that there is multimodality because the MCMC chain might be only exploring a mode, or we know it's slow, but
But which is normal, and actually,
yeah,
that
yeah,
that's actually one of the deterministic people say your chain is
mm,
never really mixing. And
mm,
maybe if you're using some sequential Monte Carlo, it isn't. You made me think of a incident and a question actually, which is kind of around the posterior of a mixture model. I was working in the same office as Peter Green a long
mm,
time ago, and I told him Christian Robert had blogged about mixture models, and he came up with something I found really left field, which was that the parameters of it are not should be a point process.
mm.
And I'm like, okay, I can see that. I couldn't work out if that was smart or just restating things, if that actually affected the computation. I don't know if you got any comment on that. It was just a
No,
random
it's
thought,
it's
but
it's a it's a nice way of visualizing the posterior because of a nice way to think about this
but
and
the
that permutation and variance in the posterior.
exactly. I suppose if you could,
Mm.
but it's not very nice to compute with a point process. But
Oh, it does not change anything in that respect,
yeah,
but it does suggest some other ways to plot. For instance, you could, if you have a mixtured model with different components, what you can, let's say they are univariate Gaussian, and then you plot all the pairs of mu and sigma, and they give you different clusters.
yeah,
And that's a smart way to represent the posterior. And it's a bit like this point process representation. You
yeah.
don't really care which one is one, two, or three. You just say, I mean, yeah, you don't make a difference between the point. You just represent the mu i, sigma I that are being simulated. And you'll see different clusters that correspond to the different clusters in your data.
Right. There's the whole label switching thing, and
Mm.
I mean, I think I was always of the school label switching is not really it should happen. In fact, if the sampler is working right. But
That was
I
Christian's
think
view
Peter
in
Green
this
was
famous
saying
paper.
the problem doesn't even exist. Um, And from memory, Redford Neal threw in a comment which was don't add in a transition that permutes, which I couldn't see how that did harm, but maybe would break diagnostics. I don't know.
It has been a long time since I looked into these papers, but
Yeah.
I
Yeah,
mean,
maybe
the
mixed
problem
trees
is
are a lot less
everybody
fashionable than they
everybody's
used
right.
to
It
be.
just depends how you view the problem. And
Yeah. Okay.
mm,
Um, Let me see to um okay, well, I mean maybe this goes back a bit to where we were, but there was an advantage of SMC is you can compute marginal likelihoods.
mm.
Some people like Bayes factors and marginal likelihoods, and some people don't. Is it again, are you going to dodge and say, shut up and compute, or do you have there's Andrew Gellman's model expansion idea. Do you think marginal likelihoods are important?
I hope so because that's one of the main selling point of SMC. It's funny because last summer I was invited at a nested sampling workshop. So nested sampling is this method which is popular in physics, and it was invented by John Skilling. And
Okay, yeah.
nested sampling is also something where you estimate the marginal likelihood. And these guys, they really like nested sampling because of this. They really like the idea of computing marginal likelihood and comparing models. It makes a lot of sense for them. Sadly, they still want to use nested sampling. They don't want to switch to
Okay,
SMC, but I try to convert them.
okay.
But this is important to them. So it depends on the community. Again, when I was talking about this collaboration, I try to have with a more applied statistician, like my friends at INRAE, which is a French institute of research in agronomics, stuff like that. I'm not sure that's how you say it in English, but um, well, when I work with these people, where they develop scientific models and they actually want to compare them or see if they can simplify the models and they do use marginal likelihood. So I'm glad if it's useful to some people, and because again, that's something you can do with SMC samplers, but you cannot do otherwise.
Yeah.
Mm,
I mean, I think it's at this stage, some of it is a modeling question of, and I think to me, I think I agree that saying pro-bit versus logistic regression is a bit silly,
mm.
perhaps.
I
Um,
I think one essential thing we do in statistics is I think model comparison is actually quite important in respect of trying to stop when your models get crazy, like you add more and more parameters. And that's one of the things where sometimes when I look at Andrew's position, I'm not sure I completely agree because Andrew likes to make model more and more complex. And I mean, if you compare marginal likelihoods, and then the marginal likelihood of a more complex model does not favor this more complex model, is tells you have to stop. The data does not support this level of sophistication in the model. I think it's
okay.
important in stats because that's what I mean. Statistics are mostly about saying, "Oh, look, this is just what you're looking now is just noise. Stop. It's time to it's time to
So,
do something else."
okay. I think
You
he
see what
quotes
I mean?
Radford Neal of saying that you should maybe infinitely complex and these are people kind of that go in the direction of Bayesian nonparametrics and um,
Mm.
it,
I yeah.
it,
Is yeah.
there's a taste here also. I have a question from Tom Lauder, which is Nicola wrote a paper with Christian in 2010 that was critical of nested sampling. What is his view now, especially after attending the NS workshop?
Right. So nested sampling works. It converges when the number of particles, let's call it like that, go to infinity. It gives the right answers. There's a nice paper by Leah Sorf and Chris Drovandy, and maybe Adam Johansson is involved too, if I remember correctly. They try to compare a nested sampling with SMC, and they also come up with a nested SMC algorithm. And they have a compelling numerical experiment that show that using SMC, even in the or nested SMC, work better than vanilla nested sampling. And so, and I try to replicate independently some of their results because I wanted to play with it to prepare this talk last summer, and I wanted to implement their nested SMC algorithm in my particles package, and I found the same. So nested sampling is okay. It's just I'm pretty sure it's suboptimal. You should do SMC instead. At least the nested SMC seems to beat vanilla nested in all cases. And it's quite intuitive why. I mean, I could elaborate, but so nothing wrong with it. It's just it is not optimal, I think. But again, what I found interesting last summer is that people really cared about this method because it gives them the evidence first, and
Right.
second, this is something they understand. They invested a lot of time in it, so I can appreciate that. I mean, in a certain field, people have invested in a certain method.
The
Why not
This
after all?
Cambridge school, like in machine learning, David McKay, I think is very known for this idea as well. Um,
Mm, but
but
there's a lot of people in physics that got convinced. I mean, I didn't know all these people, but they're from Germany or other places. There was a guy from New Zealand that came only for 1 week.
okay, well,
He was completely jet lagged. So anyway,
the
why not?
but I'm assuming that there's a type of model where the marginal or the evidence and the marginal likelihood is, that you have two hypotheses of like two models that look completely different to each other. So is that the type of problem they were working on?
I'm not sure. I'm not really sure. I prefer not to say. You should
Okay,
ask
fair
them,
enough.
but
But
yeah.
they had their way of thinking about it that
Yeah. But
uh,
their models are physics based, so yeah, there are some. I don't know. I don't want to talk about something I'm not an expert, but yeah.
yeah, I mean, I think my assumption with Andrew's statement is more, it's not that it's no model. He's not working on problems that look like that, that are
Mm,
too. I think my example is silly probit regression versus logistic regression, but there might be a version of that that's sensible,
mm, mm,
and
mm,
and especially in physics, that
mm,
would be
mm, mm, mm.
my guess of why it's taken off. Um, do you want to tell? So one of your latest projects has been the particles software. That
Mm.
do you want to tell everybody
Yeah, I mean
this?
it has been fun. To be honest, I'm a geek. I mean, I like implementing things Python, but if you do it for the community, change a lot of things. You have to be more careful about
Do,
documenting things.
do you want to tell everyone what it does first? And well, me too.
Yes,
Actually, I
sorry,
only know
sorry.
I
Yeah.
only know it
So
exists. So,
so with my friend Omiros Papaspilios-Poulos, for several years we were working on this book on sequential Monte Carlo, and I did all the numerical experiment in the book, and in doing so, I started to develop all this example into one big package. So this is a Python library where you can implement particle filters and related algorithm, particle smoothing, Kalman filtering, and also sequential Monte Carlo samplers. And yes, it's my objective now is try to be quite comprehensive, so to try to implement everything that exists so that people can maybe use it as a reference, and if they come up with a new method, they can compare it, etc.
so it's a package for people doing applied statistics or people that are innovating computational statistics or both.
I think the way at the moment I would say is more for people who like to develop algorithms, and
Okay.
it's I will be very happy if someone from applied stat use it. And actually, I got in touch with some people like that, but I'm not. I'd be happy to interact with people if they could tell me that how useful it is for applied statistics and how easy it is to use. The problem when you do open source software is that when everything works, nobody tell you anything. People get in touch only for problems, you know. It's a
Okay.
bit frustrating. So,
I
but
guess you can see people are cloning the repo or something
uh,
to give some track of activity. Um,
mm, mm.
Maybe that brings back to another topic is like, what are your thoughts on probabilistic programming and other sort of stats tooling? Are you so good that you never use it, or
I will not say that, but it's funny you ask because I was invited in. It was a bit embarrassing because I felt I knew nothing about it, but I was invited to give a talk at a probabilistic programming conference at Collège de France in Paris, which was nice because I mean, you should visit Collège de France in Paris. It's free. You can visit at any time, and there are talks, scientific talks, all year round. And that's the first time I go. Shame on me. And um, and I tell these guys, look, thanks for the invitation. The thing is, when you're someone like me, you're trying to develop new algorithms and all these probabilistic programming tools, they're not direct. I don't know how to use them because they seem to be designed more for people who don't want to design algorithms, or for applied people who come up with a model and they want the software to implement certain methods. They don't even know, they don't even want to know which algorithm are used. They just want to come up with approximation of posterior, which is fine. But when we're trying to develop new algorithms and see if they work better, it's my impression that these tools are not directly useful to you. So that's why I tell these people. It was a bit, I'm not sure it's super useful to them, or I don't know. But maybe in the future, these tools will become so powerful that it will be useful for
I
both
think
for
there are
practical
people that would
and
say the
for.
future's been here a while
Mm,
I mean, the only one I use is like I use Stan and have you for a long time, and
mm,
it's very good on certain problems.
mm,
It's not very good when there's multiple modes. I have to, in my opinion, hopefully I'm not offending anyone, but you certainly you can get very good performance and change it a little bit and get very bad performance.
mm.
I think
On the
if anyone
live,
disagrees, then
mm,
I'll let you speak. But
the Live Pima Indians Alone paper, my collaborator, who was my PhD student, James Ridgway, it took him much more time to use TAN to implement nuts, the nuts algorithm. It took him quite a lot of time, and he said, I would rather re-implement the algorithm in C. It would be less work for me than to get into it. So it's funny. It's a
this is a
funny
very
comment.
specific profile, I think.
Exactly, exactly. I mean, it
Yeah.
really depends where you're from, and I mean, for
Um,
me, if I want to run HMC, I might implement it myself on Python because it might take me less time that to try to understand how to use Stan.
you'll
It's not
do
a comment about Stan. It's just, I mean, what is
and you'd
difficult
rather
really varies from one person
do
to
the
the
vector
next.
calculus all yourself
Yeah.
than use autodiff. I'm not entirely joking. I think that you
Mm.
might.
No,
Um,
I mean, I will try to use autodiff now these days. I mean, it's better practice, I guess. It's best practice to use these tools. Yeah. Mm.
I,
But
I I don't know the circumstances when it's faster and when it's just easier, to be perfectly honest.
mm,
But there are tools that so I guess there's AutoGrad in Python, which is that what you're using, or
I'm
do you
looking
get
into it
PyTorch
like a
and
Jax, for instance.
okay,
Jax looks like
okay,
pretty good, but I've just played with it. It's not in particles yet, for instance.
okay.
Mm.
Um, let's maybe turn towards some machine learning topics as
Yes,
um,
controversy.
I'll try to get controversy once more is well congrats on your paper, by the way. You had a paper accepted, was it yesterday, with two
Yep.
people for Criteo, my student and my past student, both excellent. Uh,
Thank you.
but on statistical learning theory, not Bayes at all.
Mm.
I keep telling them they should do Bayes, but they won't listen,
I
and I
tried.
feel
I
they might be
tried.
right.
I tried to make Hotman work on SMC. I did try.
Yeah, yeah. But I mean, they know their own mind, both of them, and it's great.
Mm.
So do you have a what do you think on Bayesian decision theory versus statistical learning theory? Do you just say
Ah,
these
okay, that's a tough one. So you said between Bayesian stat decision theory and
and statistical learning theory?
um, I
You
don't know
just
to be, yeah, I'm not
they're
sure.
both interesting. You study them independently. You're not
Yeah,
bothered
yeah.
by contradictions.
Again, I'm not a very philosophical person when it comes to applied mathematics, but
Okay,
yeah.
okay, that's fine.
Mm.
I've failed again to get you to say some controversial things, but I can try with well, what are your thoughts on machine learning as a field and
It, it
what's interesting about it? Where is it all hype? What does it have to bring?
it's it's a bit challenging to have both for machine learners, I guess, and statisticians to have these two communities that are so close yet so different in terms of how they publish papers. And I find it a bit frustrating at times to see because they operate and publish much more quickly and because of that, I can see that some papers they kind of sometimes repeat some mantra and they are all agreed on certain things like, oh, well, let's do gradient descent, stochastic gradient descent, it works, or let's do neural networks. And it's, but
Okay, sounds like
it, it,
you might want to say something to contradict these mantras then.
no, no, but I don't, I don't, I don't want to say they're wrong. I want to say it's not very scientific to say mantras
Yes. Okay.
because sometimes they are so vague. But it's not they're true or wrong. They're too vague. It's not they're not even wrong. It's it just yeah. There's something a bit too. But I mean, anyway. I mean, of course, it's a frustrating. But what can you do? Ignoring what's going on the other side will also be silly. So I mean. What is my concern in practice is mostly for junior people these days. I mean, if you're in stats, um, should you try to have at least one machine learning conference paper or not? It is something that is more or less. I mean, if you apply to jobs, it's becoming a requirement. Is it a good idea? I don't know. I mean, do you want to go on 100% to machine learning? Do you want to stay in stats? What is stats? What is machine learning?
I was about to ask you this question
Mm,
actually.
Yeah,
Uh,
I don't know. I mean, it's a tough one. I think they too crash. I think, especially when you're in computation like myself. Uh, I have this recent paper which I'm going to advertise. Sorry, but
That's why you're
we
here. Go.
yeah. We have a new method to estimate ecological inference models. That's a kind of problem you do. So imagine, for instance, in the US, you have different counties, and each county, you know how many people voted for Trump versus Harris, let's say, for the next election. And you also know the number of white people, black people, and the number of people are employed, unemployed. So you have this marginal distribution for the different categories, but you like to study the fact you're employed or unemployed. How does it change your propensity to vote for Harris versus Trump? You know, that's the ecological inference problem. And in France, we trying to apply it to two rounds election, like the president election. So in the different polling station, you know how many people voted for candidate A at the first round, and how many people voted for candidate B at the second round. But of course, you don't know how many people voted for A and B. And you'll try to estimate the propensity of voting B at second round, given that you voted A at the first round. And so It's a very nice project, and we had with Robin Ryder, we had a very bright undergraduate student who came up with very nice ideas. This is a stats paper, I think, because ecological inference has been a challenge for a long time in stats, and it's of interest to social scientists. And that's the kind of thing that statisticians do. And the way we do it is, I don't want to divulge too much, is the paper will be on archive maybe in a few weeks, but it's really using tools that are familiar to statistician. So I would put that in stats. Whereas in machine learning, the objective, I mean, everybody knows machine learning is mostly about classification, and I mean, I appreciate that in machine learning they have a clear metrics about this method does better this one because on the data you have this score, etc. But stats is not only about that. I think it's also about estimating parameters that have some sense that you want to interpret, and etc. etc. That said, maybe in a few months we're going to do a machine learning paper, which is a follow-up of. So it's a very good question, and it's a difficult one. The limit is kind of blurry these days. What is clear is that the way we write papers is so different. And it would be a shame if the machine learning one was the only one, I think.
How would you
Mm.
describe that difference?
Oh, because I'm just pointing on the fact that we have journals and they have conferences, and when you submit to journal, it takes much more time to get your paper accepted, and the papers tend to be longer, and all this kind of thing, and the review process in machine learning is very something a bit random. I think it's a bit
Yes.
worrisome, but so yeah, all these things. So I think yeah, I can see why they do it this way, but I still prefer the stats way, to be honest. And I hope we can preserve that. And
Yeah.
if someone wants to do a PhD these days in anything related to what I do, my recommendation is maybe to write one paper in machine learning conference because it's becoming a requirement for application, but the rest publish in stats. Unless you want to be 100% machine learning, and that's fine too. But it's
Yeah, I mean, I think some of it is marketing for your if you're
mm,
wanting to turn to industry and so forth. But I
yeah, it depends what you want to do next. Mm. But
yeah.
it's yeah, it's I'm a bit worried about the following years for machine learning because it doesn't look sustainable in terms of the number of submitted papers. It goes up and up at an exponential rate. So, I mean, it's not
The review
sustainable.
cycles are fast, which
Yeah.
it's good in some ways, but it's hard to do good reviews so fast for sure.
And and I mean, it's getting more and more difficult to recruit referees. So you end up asking even undergraduate, and that's a bit crazy, I think. It's a lot of responsibility for undergraduate to evaluate machine learning conference. Mm.
Yeah, for sure. I mean, I guess we may be landing the same as deterministic versus Monte Carlo. There's both have things to offer.
Mm.
On the ecological inference, did you encounter the modifiable areal unit problem as well in that space?
Did you? Sorry, didn't
It's
get it.
the modifiable areal area unit problem, which is,
What?
I think,
I'm not
it's
familiar with.
it's like the PE equals NP of geography of
Ah, yes, yes.
you know what I'm
Uh,
talking about.
yeah, yeah, yeah.
It's say you're doing census measurements, or you have one data by I don't know the census districts and another by postcodes, and you want to put
Mm.
it together. This is
We didn't deal with this problem in any way. No.
it's very
Yeah,
related, I think.
yeah. It is. It
Um,
is. It is. Yeah.
yeah,
But the Theo, the student who is one of the authors, might know more about this because he comes from. He has a strong background in social sciences, and yeah. Um, the nice thing about French data is that you have all this pole station data. So, and yeah, so you just assume that there's a probability to vote B given A at the first round are kind of constant in a certain region, then you can estimate them quite accurately. But it's a model, of course. It's you might agree or disagree with the model. That's another story.
It sounds interesting.
Mm,
I dabbled in this a very long time
yeah.
ago.
If you are interested in French politics, we have interesting findings.
I must confess, I do not understand French politics at all.
Yeah,
So, but
never
that
do I.
gives you another angle on Andrew Gilman does the same, or
Uh,
Nate Silver and so on.
uh, uh, uh.
So where are we? So what problems are interesting? I guess we're on the hour, but we can keep going if you.
Yeah, I don't have anything of super interesting to say, but a lot about SMC again. I think you have still stuff to be done and more applied stats. So this ecological inference is a problem, is an example of that. I'm doing a project with colleagues in genetics as well, where they came up with a state space model and we can do particle filtering and PMCMC, this kind of stuff. I really like this kind of stuff. Um, a little bit of everything. I'm not a very disciplined person. I don't know why I'm working on certain things at a certain moment.
Sorry, you don't know if you're.
Yeah, I mean, I just don't understand. You know, when you're supposed to to apply for grants, you're supposed to say you have this big project for the next 10 years. It's just not me. I mean, I really don't know what I'm going to do tomorrow. But I don't know how people do it. I'm impressed actually. People come up with. So Michael Jordan gave a talk in Venice a few months ago with this big, very ambitious project for redefining what is machine learning, and that was I find it very interesting and thought-provoking. And I'm not a person able to do something like that, but yeah,
I
like
never
this
had to do the
vision for
grant
the
writing
next year.
game, and I'm very grateful actually when I've
Mm,
seen people put all their heart and soul into things, and then
mm, mm, mm.
they often get rejected and so on.
I think we have
Um,
questions actually, but
the more comments we've got ML statistics for making pretty pictures. I don't know if you you can respond to that if you want.
right,
This is your opportunity to.
ML is statistics for making pretty pictures. What do you mean, Adrien, exactly? I mean,
I
you mean ML has pretty pictures or stats has pretty pictures? I guess stats have better picture, no? I don't know.
I feel there's good ideas and bad ideas in both, and good work and bad work
Yeah,
in
sure.
both. Um,
Mm,
and then often I think stats people either think ML is completely foreign and they have nothing to add,
mm,
or it's complete rubbish.
mm.
So I think that I'm not a fan of either. Um,
Eh,
and
you know, once we came up with the idea of a stats challenge, a bit like a Kaggle, and in the end it turned out to be a bad idea because again, the nice thing about machine learning is really easy to define some to do a competition because everybody agree what are the metrics and you have to beat a certain all the other teams, etc. But in stat, it's much more difficult to come
why
up with a challenge like that.
why is that?
So I don't know, but I mean, for a certain problem, instance, you have many different approaches and each one with the different drawbacks and merits, and it's much more difficult to just, I don't know. It looks to me more difficult, but it's, I mean, there are a lot of situations where people apply statistics or develop models or whatever, where it's not really clear what would be the metric for one approach compared to others, I think. So that's one, I mean, that's one positive thing to say about machine learning. They are
I feel like you're now
very clear.
starting to become philosophical.
Yeah, yeah. No,
And
I
yet
mean, it was my experience based on this one case where we tried to do a challenge. in the end, it was not, I mean, it didn't work really well. We proposed some image and we had some question and people had to come up with models and well, there was only two teams competing anyway and one team said something really bad. But still it was, yeah. I mean, if some people here have some ideas or to do a stat challenge, I would be interested, but we didn't do a good job in the end, I think.
I feel this is topics become a bit fashionable, as well as the Premier Indians. But I mentioned there's Morris Hart did a talk at, I think at ICLEAR, and I saw it at ECML, where he was all about benchmarks and
Mm, mm, mm,
talking about, and well, MNIST I think is the equivalent of machine
mm,
learning and ImageNet and so forth. And Ben Rector, so I think has worked with him in making similar points of basically very pro benchmarks and for like ranking classifiers with images and so on. And um, this makes some sense, but I think there's maybe I have a statsy part to me, in fact, which is because firstly in Rexis, these benchmarks don't work very well. So
mm,
most of the problems I'm in, because they have a bit more of a causal, it's not super easy to benchmark recommended systems or contextual band or anything more. But I think there's a more complex questions of like, well, if you're analyzing a randomized control trial, you really care about the data and the results on this. But either in stats and machine learning, I'm not sure they're different here, is when you're just trying a data set, it's a
mm,
more
mm,
abstract question you're asking is this algorithm or method extracting something useful? And
mm, 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 mm.
um, it's
Exactly. Mm,
it's not the same question.
mm, mm, mm,
Anyway, that's my um, my commentary on that stuff. But
mm. I try to, I mean, when you work in computation, you can always, as you say, shut up and calculate. That is, this is some data people use, this is some model people use, this is some prior. Look, my method for this combination of the two does better in that respect, and we have clear metrics, and look, that's
that's
it.
also true. In fact, I was about to mention this is of who can compute an expectation
Mm,
more accurately or quicker,
mm,
or
mm.
marginal likelihood or something similar.
Yeah.
And,
If you just look at computation, then it's quite clear, just CPU versus approximation error. Mm.
um,
Plus maybe
you need to believe in Bayes for this to be important,
mm,
uh, but yeah, I think the benchmarking, there's a more notion of you're experimenting by running algorithms, and it's
mm.
a bit more of a complicated question. But I mean, is it not possible just to run a machine learning challenge in a machine learning way in stats, or is that not stats?
And we can try, but the only time I tried, I was quite unhappy about the result. I mean, yeah, I mean, I think again, if you just have something where you don't define the model, you just give some data and ask people what will you do on this data, you might end up with different answers that are, some of them are different but useful, and I don't know. It's become difficult, I think, but
Yeah.
to have clear metrics. Unless if you have something like prediction, but if a model is trying to explain some underlying phenomena as we're supposed to do in stats, then it becomes really difficult, I think. So I was working with Simon Barthelme on, I mean, he's the expert on visual perception, stuff like that, and they have different models and very interesting data, but you cannot really, I don't know, maybe the metric is what kind of journal you manage to get published with this model. But yeah.
Yeah, I mean, okay, something I don't like about stats is like, is it significant? This stuff, which people who don't know stats but do applied work, I think
Mm,
fall into this.
mm, 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 mm.
Um, um, well, maybe we should wrap up.